Changing speed of light as it goes from one medium to another makes light bend, okay? And here is a basic relationship that we're going to use. When light, oh yeah, now we're using the whole ray model. Ray of light comes in, it's in air, hits like a glass block. And what happens is it bends. It bends. And we have a relationship to describe the bending that looks like this. Ray of light comes in, hits the surface. We'll draw a line perpendicular to the boundary. Okay, so here's the boundary between the two mediums. I draw a perpendicular line, and I measure the angle with respect to the perpendicular, measure the angle with respect to the perpendicular. Ray of light comes in, bends, and the ratio of the sines of the two angles is given by this expression right here. So the angles are related to the index of refraction in the two media, okay? And so light is going to bend. And we'll use this to solve a bunch of different problems. For instance, look at this one right here. A 4-meter wide swimming pool is filled to the top. The bottom of the pool becomes completely shaded in the afternoon when the sun is 20 degrees above the horizon. How deep is the pool? Now you might say, the way you figure out the depth of the pool is you just talk to the homeowner and say, how deep is your swimming pool? Or you could even, if it's a public pool, you could look at like the depth marker on it. Oh no. That, then it would involve interacting with like human beings perhaps, and that is not the way of my people. There's a way to calculate this. There's a way to calculate this, okay? And we'll do that. Now here's the thing. The trick of these kind of problems is to make this look like this. I want to take these words and make it look at and turn it into a picture that looks like that, okay? And here's how we do it. Here's how we do it. The swimming pool is 4 meters wide, okay? So I'm going to draw, here's my swimming pool. And let's suppose it's completely filled with water, so it's filled all the way up to the top. Oh, heavens to Betsy. Then there's a boundary between air and water. And when a ray of light hits the boundary between air and water, it's going to bend. And so I'm going to have this refraction happening, okay? And we're told that sunlight, the sun is 20 degrees above the horizon. So if a ray of light comes in from the sun, it's coming and hitting the edge of it's hitting the water at an angle of 20 degrees above the horizontal, right? And then when it hits the surface of the water, it's going to bend. It's going to bend, okay? And so it's going to be doing some of a bending thing. And then the light is going to hit over here. And if I have a ray which comes in over here, it bends and hits the side. If a ray of light comes in and hits right at this edge, right here, where does it hit? Well, I think what I want is I want it to hit here. I want it to hit right there because you're told that the bottom of the pool is completely in shadow. And that means that the lowest possible ray of light that I can come up with doesn't hit the bottom. It hits the side. And so no light can possibly hit the bottom of the pool. Any other ray of light that I have that comes in hits like so. So this side entirely lit, this side down here entirely dark. Let's take that. I'm going to copy it over on a figure with just one ray, okay? So I'm going to recopy it. One ray. Ray of light comes in, 20-degree angle, bends and hits in this corner. This is a 20-degree angle right here. Oh, heavens to Betsy. I don't want this angle. I want the angle with respect to the normal, right? So I want this angle right here. That's my theta 1. And what is theta 1 equal to? 70 degrees. Oh, then I can use my refraction rules. And if I know theta 1, I can calculate theta 2. Oh, and if I know theta 2, I can say something about this here triangle. What's the length of this side of the triangle? That's 4.0 meters. Excellent. I'm making progress here. And that's enough for right now. Now I'll write down my basic refraction rule, which is this. N1 times the sine of theta 1 is equal to N2 times the sine of theta 2. And what I'm looking for is this. I'm looking for the angle of the light inside the pool. So I'm looking for sine of theta 2. Sine of theta 2 is equal to n1 over n2 times the sine of theta 1. Oh, but I know the indices of refraction. I know the indices of refraction. I have a table here. In water, 1.33, okay? And air, 1.0003. What do you say we just call that 1? Close enough. And heavens, since we're in Colorado, it's actually like 1.00025. So it's even closer. So we even cheat less. Excellent. So we're going to call that 1. So the index of refraction in medium 1, which is air, N1 is equal to 1.0. N2, which is water, is equal to 1.33. So my equation is therefore sine theta 2 is equal to N1 over N2, 1 over 1.33 times the sine of theta 1. And then if I do that, I solve for theta 2, I get this. Theta 2 is equal to 45 degrees. Theta 2 is equal to 45 degrees. So how deep is the pool? We could do a trig relationship. So this is 4.0 meters. 4 meters. That's a pretty deep swimming pool, isn't it? My swimming pool, 15 feet wide, 15 feet deep. No, it's more than that. No, it's about that. It's like 14 feet. 14 feet wide, 14 feet deep. Good thing you asked. I want to show something here. The bending of light, if you have a structure which bends light, like right here I have a prism, classic bending of light object. Check this out. I got like pH 122 written there. I slide my prism down. Oh, now I have like double pH 122. This is like pH 244 right there. Oh, yeah. And so light is coming through the prism, and some of it comes through this side, and some of it comes through that side. So light from the bottom can reach your eye in two different ways, and it gives you two images, okay? Now, you see this sometimes. If you look at an aquarium, and you look in the corner of an aquarium, you might have noticed you see light, or you can see like this plant. I can see through this side, but I can also see it through this side. And if there's a fish, you can see like a double fish. Let's talk about how that happens. And I want to talk about another piece of the whole light ray thing, which is the position of images. What your eye does when you're looking at something is this. You have two eyes. This is not a surprise. And you basically trace the rays of light back and see where do they appear to come from. So when you're looking at me, you can tell I'm standing here because your two eyes are kind of like saying, like, tick, tick, tick. This is where the rays of light coming from Brian are. They're kind of in this direction. And I represent it this way. I say, like, here's your eye or your eyes. And if rays of light are coming from some sort of an object, you trace those rays of light back and say the object that emits those rays of light or reflects those rays of light so that they come towards you is right there. And you trace the rays of light back to see where they come from, okay? And so that's another piece of the ray model. And we're going to do a lot of problems with that, particularly when we get to talking about lenses. We're going to look at like bending lenses, and then you can make things appear all kinds of crazy places. And one way we can look at it is this. If I have my fish tank like so, and I have a fish in here, and you're looking from down here, a ray of light can come out of the, like so. When it hits the edge of the tank, it bends, and it bends this way. It can also come out this side of the tank, and it bends this way, okay? And then, if you're looking from here, you don't know the ray of light is bent. Your eye just traces it straight back to see where it comes from. What you get is this. True rays of light trace backwards. And so it looks to you as if there's two separate objects. But in fact, what's happened is the rays of light can just take two different paths that lead towards your eye. But the key fact is this. Whenever you're trying to figure out where something is, you trace a ray of light back and see where does it appear to come from. And that's how you locate an image. Given that, I want to think about this. Let's look at this problem right here. So I have a heron fishing. Fish is 10 centimeters below the surface of the water. Does the fish appear to be at a greater or a shallower depth than this? Okay, so we want to think about this. Let's see how I would solve this problem. Here's the surface of the water. Here's a fish. And we'll make a smiling fish, because like unaware that it's about to be eaten, okay? Unaware of impending disaster. Ray of light comes off the fish, like so, hits the surface of the water. And when it does that, it bends. Now, the case that we looked at, where we had light going into the water, it bends to a smaller angle when it's going from air into water. And so when it goes from water into air, it goes towards a bigger angle, okay? And so the light bends away from the normal. It bends like this. And then another ray of light comes off this side, hits the surface of the water, and then it bends. And again, it bends to a bigger angle, like so. And if the heron is up here looking down at this situation, where the fish appears to be is where the rays of light are traced back to. So we trace them back right here, and the light appears to come from that point. So what can you say about the apparent depth? Does the fish appear to be 10 centimeters below the surface, less than 10, more than 10? Less than 10. And you might have noticed this. I love to walk in really still water, like knee deep, and look at your feet, because it makes your calves look really like foreshortened. It's like your feet are closer to your knees than they're supposed to be. And I really quite enjoy that perception. So go ahead. And this is, it's a big deal. Now, the heron is able to compensate for this, because if you watch them catch fish, they know where the fish actually is, as opposed to where the fish appears to be. And so they're like solving this optics problem, kind of like as they go, and they have some way of compensating for it. And it's not trivial. If you've ever tried to like spear fish, which you probably haven't, but if you do, it's just not trivial. This is not a trivial thing to do. Here's another problem. The apparent size we have of things, and this is something that we'll talk about, relates to how close the object is to you. And if something's close to you, you perceive it as being big. And if it's far away, you perceive it as being small. And so you can have kind of interesting, this is a nice picture that someone took where they're like utilizing a cloud. And it looks like a single picture. Well, it was a single picture, but it looks like you're spraying a cloud or something like that. And this is just because the can's close, and so it fills up a lot of room. It's big. The cloud is far away. And even though the cloud is gigantic, it's far away, and so it appears small to you. Closer is bigger. And we'll have a lot of things to say about that when we look at magnification of images. So if you look at something, and this is a picture which is from the textbook, ruler stuck into a fish tank, like so. So ruler in a fish tank. And then the ruler appears to be closer to you. And there's kind of like a discussion in the book about how you do the rays of light. It's the same thing as the fish problem. But the net result is this. The ruler appears to be closer to you. And because it appears to be closer to you, it appears to be bigger to you. And it's bigger not because it's magnified. It's just bigger because it's closer. I mean, it's not like a lensing effect going on. It just appears to be closer, and so it's filling up a bigger swath of your field of view, and so it appears larger to you. So closer is bigger. Okay?